Welcome everyone, my name's Mark with Advanced Assembly and I'm here for Mark Voids a Warranty. This is the favorite part of the week where I just get to destroy stuff, some of it expensive. Today's stuff might be expensive. If you have any thoughts, I've got some choices there in the chat for you. Feel free to jump on in there and select something. I'm more than happy to take apart what you guys would like to see. So, before we get started, I do have something to show you that you might find interesting. We recently released something we call flexible footprint to address the current part shortage. I'm going to put it on microscope here in a second, but we came up with some land patterns that will allow you to basically create anything you want for as far as rectangular passive sizes go. You guys can combine 0603s, 0805s, anything along those lines. So let's take a quick look at that. And we need our microscope view. So typically when you make a part, you just choose a standard land pattern size, but it turns out that you can actually combine these and get, might make more sense if I do it sideways there. You can combine these and get a land pattern that'll work on a variety of parts or with a variety of parts. So for example, you can't find a 14 microfarad capacitor in an 0805, maybe you can find it as an 0603, right? Who knows? So take a look over at our blog, aapcv.com/blog, and you'll see a little write-up on that, and we'll try to help you out. All right, looks like we don't have any comments just yet, so let me skip over to our down view and I will show you what I was thinking today. We've got two cameras, two machine vision cameras, and I think I can get a little closer for you. One, it's this Telesign Dulce Genie, model number M1600. It looks like. And then we've got Keyence CAHX200M is the model, and it's the 16x2 Mega. So high-speed camera. If I remember correctly, this guy is like 1600. This is the Teledyne. It's like 1600 pixels wide, and it's like 15 frames per second. Versus this guy, I really don't remember the specs on him, but I believe the 16x refers to the 16 times speed. And before we start tearing these things apart, as I like to do, let's take a look at these image sensors. Right on the left, this one that's moving right here, that is our Keyence, and that is a huge sensor. On the right, that is our Teledyne Dulce, and that is a much smaller much smaller sensor. The reason that you like bigger sensors for, all things being equal, right? Same pixel count, a bigger sensor is going to receive more photons and therefore have better performance in lower light situations. And you would have a lower light situation if you went from something like 15 frames per second to something, and I don't know that exactly how fast this goes, but let's call it 300 frames per second, 1,000 frames per second. You want the bigger sensor so that you don't have to have this thing flooded in as much light. And we're seeing some reflections there of yellows and cyans and greens, kind of pretty. So let's start with the slower one here, the Teledyne Dulce, and see what we've got. Feels lighter. It's got mounting holes on the top and bottom. I don't know if those are metric or what. And then it's got 4K screws that I can just pop out with a spline driver. And I can't imagine putting this one back together, but you never know. Keyence, I might. I think I need to take out all my aggressions on this one. Play Mark Smash over here. Let's see what we got. Okay. So I've just loosened the screws. We've got an FFC cable that's connecting the front to the back there, and there's 2 boards in there. So I'm gonna withdraw those long case screws. And then we're gonna flip the little lever, securing lever here on the FFC connector. These little ZIF things are a little different. Well, let me just get my finger under it or see which way it goes. Oh, it's flipped up already. Okay, I already flipped it up. So this appears to be our image sensor and processor. We'll take a look at that in some closer images here in a minute. And then on the other side, oh, we've got all sorts of stuff. So on our other side, we've got 2 boards, one with, you know, some inductors. So I'm guessing that's going to be our power regulation, but that is an awful big IC just for power, so I don't know what else is going on there. And then on the back side, we've got some big chips, lots of gates on those things. So right now, the only thing that's holding us together is that back connector. I've got to figure out. I mean, I'm perfectly fine playing Mark Smash if this isn't going to come apart quickly. But looks like... Okay, so to me, it looks like this board is soldered on. This is the back side of that power and I/O connector. And there's a piece of, you know, flexible PCB material there. There is a threaded connector there, but I think that just pulls this, you know, keeps it in position. I think loosening that does me no good. But I don't see any way to pull that off at this time. Looks like I'm either going to have to play Mark Smash or I'm going to have to play Mark Desolder. Let's might as well start with Mark Desolder and go from there. Because this board is kind of interesting. It looks like they went to the trouble of making a true rigid flex board, which is kind of an expensive way to go. So all I'm going to do here is drop some solder wick. Let's see if I can give you guys a little more light. I don't know if I can or not. I guess not. I'm going to drop some solder wick on top of these and hit them with an iron and see what happens. Hopefully the solder will get sucked into the wick and we can start releasing that board from the connector. Not yet, though. Not yet. Let me get something of a pry tool. Get underneath there. So I'm still going to use that desoldering braid. And I'm going to see if I can't suck up some of the solder from there. Although if this is a ROHS part, I'm going to have to increase my heat some. And if this doesn't work, the next thing I'll try is a hot air gun. And I don't seem to be sucking up much solder at all. So I could be low on temperature. If this is ROHS Rojas, then that would explain it. So we're going to let the heat gun come up to temperature. And see if I can't get a tiny bit more light on that for you. Let you know what I'm working on. So that multi-pin array is what's going to have to give to get this board out. I mean, that is real interesting that it would be designed in that way. It would have to be assembled in place. Which would be kind of a pain in the butt from an assembly standpoint. If I could be wrong. Looks like our heat gun's at temp. So all I'm going to do here is just apply heat while prying. Except let me see if I can do that while giving you guys a view of what I'm doing too. The reason that I'm flinging it around is it is now rather hot. I'd be happier if this was secured to something, but 'tis not. Gonna have to get some gloves here if this doesn't work anytime soon. I am just looking for an indication that that solder's melting. There we go. That part is hot. So this connector, I mean, the part's still a little too hot to handle right now, but that connector really does look like the board had to be soldered in place. That is not ideal. Let's see here. My suspicion is this connector is going to go through the other side. It's going to punch through the back side. So I'm just trying to loosen it up since I don't have a nut driver around. That is of the proper size. using my very favorite vampire pliers. That's still a little warm. All right. All I'm doing here is just trying to work that nut around. And confirm my suspicions. And if I am right, then these guys messed up pretty good. Let's see if I can hold that in position. Nope. But the good news is it's no longer trying to burn the flesh from my skin or remove it from my thumb and finger there, so I can spend a little more time tweaking it. Come on. Come on. And those of you out there today might be wondering why you're watching me work so hard on a nut, and it's because I'm hoping to show you something. And I've already invested this much time. It does seem silly to give up now. What is that, the sunk cost fallacy? Come on. Nope. Okay, it's going to be that way. But this connector is designed to go down through the bottom of the case, which then means for this design, they had to solder that in tight quarters after this thing was assembled and inserted. That pretty much takes a person to do. And if you have people doing that type of stuff, well, it's going to cost you money. With everything else they had going on over here, it kind of would have been nice if they would have figured out a way to not do that. You know, they could have done a press fit connection from here to here. This design, and let's back up a little bit. So this design is actually a rigid flex PCB. These polyimide layers go to internal layers inside these boards. It's part of the stack up. So they had to come up with special tooling to hold all these things. And that's not so bad. It's not so bad. But this would have been a pain in the butt. That tiny little board, you know, you can see some mouse bite breakaways. They just didn't have a whole lot to hold this with. And then it would have had to have been folded up. Well, I guess it would have had to have been folded that way, inserted onto the back of that connector, and then soldered, and then folded up the rest of the way. It wouldn't have been convenient. But let's see what this little camera did, and if there's anything in particular that made it special. And that's going to be an interesting board. We'll set that aside for just a second, and we'll start with the sensor module. With a smaller screwdriver, probably this one's too small. Nope, that'll work. By the way, I do have a comment window open that I glance at somewhat frequently, not too frequently. If you have any questions as we go through that or any suggestions, please let me know. And I have created a new feature for Mark Void's warranty. Commercials. Right? Well, not the kind you're thinking of. It's commercials for some of our webinars. It's just telling you about them. All right, so what we have here is a piece of milled aluminum. So this was custom designed for their product, solid. And here we have our image sensor. It's fresh with one of my fingerprints. Let's get that one under the microscope and see what there is to see. All right, so as I go over boards, I just kind of like looking around and seeing if anything catches my eye. One of the things I'm looking for are good design practices, and another thing I'm looking for are bad design practices, and I always hope to share those with you as I notice stuff. So this is the board with the image sensor on it, and there is our image sensor. And you can see the die bond wires that connect the sensor outputs to the frame. Right? Those connections come out of the lead frame, and then they start going around the board and doing things. And sometimes you can get good design practices out of this, and sometimes you don't. So one of the things that I notice, it's just an unusual choice, but it's a completely legit choice. I'm noticing that they used copper to create information on the board. Now, that is something that you do see quite a bit, but usually when you see that, the designers go to the effort of eliminating the silkscreen layer, just because it is an added cost that you don't always necessarily need to incur. You can see that everything here is ENIG, plated electroless nickel immersion gold. Almost looks like hard gold, but I don't think it is. And just a few things, like you've got these little things in the corner called fiducials. They're for aligning things during the production process. And nothing stands out too much. We've got some analog device here. I don't really know what it is, but that sure does look like Analog's logo. Quite a variety of trace width selections. That's an interesting neck down approach from what seems to be a transistor switch to a resistor. I'm looking at the connection from this device with topside marking LTGC down to this resistor. And there's a via there in the middle, and that's cool, but what's interesting to me is that they necked it down. I don't know why. That's interesting, though. I'm sure there was I would assume there's a deliberate design decision there, but man, I don't know what it is. If you do, let me know in the comments. It looks like a lot of these traces, or a lot of these pins, aren't being used on whatever this IC is. Is that a Fairchild? I don't know. We could Google that. I like that they're using nice big vias. You don't need vias that are huge, but these guys do seem to be pretty big. The nice thing is that the bigger the drill, I mean, if to some extent anyway, the less it tends to wander as it goes through the board. The real narrow drills seem to have the issue more than anything else. So nothing really all that exciting here. Looks like we've got a board that's populated completely with through-hole vias. That's good. That's inexpensive. Flipping it over. Looks like there's schmutz all over the board. So this board hasn't been cleaned, maybe because of the LCD. Some transistor. I don't know. There's not a great deal going on with these ICs as far as connections go. There's a lot of unused pins for some reason. So I'm seeing more of these traces that are changing size and whatnot, like around this 1003. And the only thing I can think of are net rules. So maybe on the right side of that resistor, and again, it's this one with top side marking 1003, maybe we're connected to ground, and on the left side, we're connected to whatever net that's connected to. That might explain the changes in size. Man, I really don't like to see that. I would call that something that you would want to fix. And let me point out what I'm looking at. Let's see if we can get a little better focus for you. Okay, so right here, we've got vias that are connecting pins. So traces that are connecting pins together, and then we've got vias in there as well. Well, one of the troubles that you run into is that vias can wander, right? This one is really well centered, but they're not all going to, even in the same batch on the same board, they're not going to be all that well centered. So the designer here put in a teardrop so that if the drill wanders in the direction of the trace, no harm, no foul. There's still going to be plenty of meat and material around. But over here and over here, we've got weird issues. So we've got some pretty narrow traces. This one's really narrow. And the designer teardropped, which is good, but they only teardropped in the direction of one trace, and that's unusual. I don't even know what software does that. Usually it's, net. You can do all the parts in a net, all of the things along the line. Maybe they did it along the line. I don't know. But anyhow, had this drill wandered in this direction, had it wandered, it could have broken this via. I mean, what I probably would have recommended is that they use wider traces if possible, or even connect these and then tee them out to the via. Interesting. So the designer sees the benefit of teardrops, but I'm guessing there's some software setting or software limitation. And that almost looks like a thermal via. So they did a copper pour in this area, nowhere else. But around these ICs, they did copper pours with thermal via connections. And I'm guessing that was just an automated software instead of a deliberate design choice again. And then we've got all this schmutz that I assume to be flux. Yeah, that's flux. That they never cleaned off their board. That can lead to latent failures. But there are reasons that you sometimes can't wash a board. One of those reasons is, perhaps water could have wicked its way into here. I don't know. All right. Now let's look at the fun one. Well, I guess let me back up for a moment and show this to you on the overhead screen. So I've got three boards. I've got the network interface, what I assume to be power, and then I've got this little I/O. We're going to look at those in better detail and figure out what's going on. On the network interface, which is the first one, we've got some pretty substantial ICs. And then we'll go from there. Let's see what there is to see. All right. So for the first one, looks like we've got another analog devices IC. And here's something that you just don't see much anymore. Well, not since the digital design revolution, but it's a completely legitimate strategy. This trace is just a straight line connection. It's, 10, 15 degrees. Most of the time you only see traces at 90s, 180s, 270s, and 0 degrees, or at the 45-degree increments too, just because that's what's set up in the software. But there's absolutely nothing wrong with you connecting point to point in the shortest distance possible. And in fact, it's probably a good thing in almost all cases. So here we've got a via with a pad diameter that is just huge, and that's another good thing for yield. If you've got the space for it, do not use your manufacturer minimum specifications. To pass class 3, you need a minimum of 2 mil annular ring. The via pad edge to hole edge distance of 2 mils on exterior layers and 1 mil on interior layers. So the bigger the pad you give your fabricator, the less chances of things failing on you and you losing a board. All it takes is one bad via for your fabricator to have to toss the board. And we're seeing lots of different design practices here. On this board, they've got just some interesting things. I'm looking for my pointer here. So you've got traces that are doing just running between some vias, and that happens. You start poking and moving stuff around. The designer used what appears to be like a tiny, I can't tell if that's a fab radius. So, the minimum etch factor, not etch factor, that's the wrong word, but the minimum etch radius that you can get out of that, or if we're looking at they just used a via with a fillet that was set far too small. As the traces move around the board, again, you can see a lot of extra copper in case it broke out in this direction. That's a good thing. And we've just got vias just kind of randomly coming out all over the place here. For some reason, we've got a tiny meander. And I'm guessing this designer felt that some length matching was in order for whatever those traces are. It's just not much in the way of length matching, especially for the speeds that we're dealing with. We've got a polyimide cover that's, I assume, providing some short circuit protection once this thing's folded up. And we're looking at the bottom side of the RJ45 jack. Altera. So this Cyclone, I believe, this is a FPGA. Another big rectangular board. The logo's cut off, but I don't recognize it, so it doesn't really matter. That's our analog chip. So one of the things that I'm surprised I don't see is copper pores everywhere. There are some copper pores on here, to be sure. But for a high-speed board like this, I would really expect to see a lot more copper pores. And then, at least a ground one and tying everything to that ground. But I'm just not seeing it. Okay, let's flip over to the back side of that and see if there's anything interesting. It's our mag jack. Okay. A field of vias. So this is the bottom side of that FPGA. Looks like they did a BGA fan out. And they did this BGA fan out with all through holes to keep costs down. That is an interesting trace. Were they trying to wander it and increase the timing? Wouldn't have increased it much. It's not a whole lot of extra distance. A lot more wanders. See, the thing that always troubles me when you see wanders, but they're tiny wanders, is if you were inside your skew budget, did it even really matter? Does your timing budget allow it? Here we can see some micro vias, right, that have been filled. See how you can see the difference between the through hole and the micro? The micros only go down to the next layer. Now, there could be 3 or 4 layers, and they could connect layer to layer to layer to layer. That'd be fine. But through holes can go through the entire board. Micro vias can't. All right. Now we've got our polyimide connector. And you can see the different traces in there. And inside, a lot of the same. Get rid of that. A little Kapton. Again, to keep things from destroying themselves when they're next to each other. You can see some test pads that have been incorporated in here. Just interesting. Magnetics, you know, inductors, stuff. Let's cruise up and take a look at this board that was giving me so much trouble when I started. So this is the connector, the input output and power connector, and it runs down here. That is an interesting copper choice. So I'm guessing one of those is ground and one of those is power, but why they split it in such a manner, I couldn't even begin to tell you. Unless that's... Is that just the trace there? And then we've got power and ground. I guess that must be... That makes more sense. So they just ran it across. Those aren't the copper. Those are just dark polyimide. Got it. Okay, that makes more sense. But that's still not a whole lot of connections. Let's look on the back side of that. Where is it? There we go. Maybe, well, maybe those are power and ground. I don't know what I'm looking at. That makes a lot more sense why we've got more pins, but then that means they have a multi-layer core. Either they did that for signal integrity or for fun. I mean, it certainly increases your cost the more layers that you have. That's more things that can go wrong. Okay, well, nothing is jumping out at me. Overall, it looks like a relatively clean board. Wind bond modem. It looks expensive, though. I mean, for a... Let's get back over screen here. For a 1600 pixel camera that only operates at 15 frames per second, that's a lot of circuitry for what it does. I don't know when this was designed. Maybe that was the state of the art at the time, but that's expensive. That's expensive. That's probably expensive. That's expensive. You got all these inductors and in the power switching circuit. Maybe if we have time, we'll come back and look at that power switching circuit later, but that is expensive. Flex, rigid flex, PCB. That is an expensive board. All right. Now let's take a look at our friend This is the Keyence 16 Mega 2. Feels heavier than the previous camera. So just a mounting plate for however you're going to put this in your machine. It's funny, I got these cameras when I purchased some lenses. They actually came screwed onto the back. I wanted the lens. The cameras came with it. These are not inexpensive cameras. But without the rest of the Keyence controller, they're not all that useful to me. Still, though, I'm not too anxious to harm this one as I was the previous one. And the previous one actually came out. The only thing that got harmed was that I/O connector. Remember, the chat is available if anybody wants to ask questions or leave a comment. Okay. So here's where we're at. Looks like we've got a couple of press fit connectors there. Much easier to take apart than the previous one. So it looks like we've got some custom polyimide FFCs, and this is our first layer of boards. Gonna need a smaller screwdriver. Now, if I knew I had to put this camera back together and there was going to be a use for it, I would certainly be wearing anti-static gloves right now. Okay, fancy, fancy. So we've got a couple boards out, covered in what appears to be some sort of a plated stainless. I don't know what that is yet. Could just be plated stainless. I mean, it's Keyence. They could be using mu metal. I don't know. Okay. That is threaded on. What is keeping that in place? I don't know. There's a ring here on the back that might be screwed on. I'm not sure. Oh man, it doesn't want to get caught. Nope, that ring does not feel like it wants to move. There could be a screw hiding here on the back somewhere. I don't see any indentations, and I don't feel any indentations. So let's stop there for now, and then we'll take a look there. This is a, I don't know what color it looks like on your screens, but on my end it looks like it's a little gold, but not really. There we go. All right. So that's free. We've got a what appears to be a heat sink material, thermally conductive something or other. Yep. Okay, so that metal plate then is a heat sink. Whatever it is, it's symmetric looking. You can see wanders right there. It'll be an interesting board. Figure out what those little guys do. Now, back to inside the camera. There's quite a few screws. Oh, looks like there's some interesting stuff on this this little FFC they have. Looks like they've got perhaps wanders there too. I don't know. We're going to have to look. Everything has kind of this bronze gold look to it. And I don't know what all that is, but I do hope to find out. So the reason that it appears that there's so many screws, some of them appear to attach all the way through the board, some of them just to attach to the next nearest layer of whatever. And I've got at least one more down there. Now I don't want to go throwing stones, but the Keyence one does feel like it is heavier. Looks like it's made some different design choices. Like, I don't know if you saw how easily I was able to remove everything. I could actually also put it back together again very easily too. Whereas that last camera, the Teardown, I would have to pull out my soldering iron to put that connector back on, which would be difficult because I kind of messed it up when I was grabbing it with my pliers while it was hot. Okay, so there is one of our FFC cables removed, and interesting, something I don't often see, but they used foam to apply pressure on the connectors. So once this thing is folded up, it pushes out, the foam is compressed slightly, which pushes the connectors firmly against each other, which I think is interesting. Inexpensive, effective. Okay. So some of this we don't even need to see pull the camera out to see. You've got a full layer of copper on the back here, a few vias that are connecting layer to layer just to make crossovers and whatnot. So this is a custom board or custom cable. This would be something you could order from a Flex PCB fab house, you know. And you've got traces of different widths and whatnot. Heavier ones for current carrying, smaller ones for signals. And you can actually create very, very accurate constant impedance traces with this type of stuff, right? The thickness is very easily controlled. There's no fiberglass, so there's no warp and weave. There's no changes in dielectric constant. So these things have very, very clean traces when you do the signal integrity tests on them. You know, you throw them in a TDR and you see if it's 50 ohms, and if it is, you celebrate, and if it's not, you wonder how bad it is. So, all right, so this is that internal board. There is some adhesive foam holding this, and it must just be a piece of copper or stainless, or maybe it's like yellow brass or something. I really don't know what that is. It could be copper. So this is one of our heat sinks that connects to the case, and this is an thermally conductive foam. Now, when I say thermally conductive, this stuff isn't miracle conductive. It's you know, it'll be lucky to get out of the tens of watts per meter Kelvin as far as conductivity goes. It's not incredible, but it sure is better than air. So if you have a high temperature differential, it can certainly get the heat moving. But the adhesive part of it is unfortunate. Okay. Let's see what there is to see on some of these boards. First one, we've got some big IC and some big things to the directly next to it, and I'm going to guess those are memory on the sides, but I'm not sure. We're about to find out. Come with me. Xilinx Spartan. All right, there's your FPGA. I don't know the Spartan 6. I don't know the topside markings, how those correspond to specifications for this particular FPGA. But we do have a HDI board. You can see those little holeless vias. Those are micro vias. All those little guys are. And this designer did opt for copper pores. So if you can keep your signals between copper planes, your signal traces between those, it can really do a lot to eliminate radiated emissions. So we're just looking around right now, and you can see caps and resistors that are connecting the memory on the left with the FPGA on the right. And you know, you've got wanders, so this designer is worried about the timing of these differential pairs. He's got spacing in between them. So where these things are immediately adjacent, they don't run in the same direction for very long. That's to keep crosstalk down. And then those guys are going to come up on another layer internally somewhere. Here we've got a square fiducial. You can actually make out very easily the warp and weft underneath this layer. Right, just because there's no solder mask or anything there, you can see the fiberglass underlaying it. That's kind of neat. All right. So there were some ICs on the bottom, but most of the parts on here are tiny and they're on the back side. So you've got a connector, all sorts of HDI vias. I'm assuming those are, well, I don't want to assume what those are. I was going to assume resistors, but I don't want to make that guess. They could be caps. And then we've got copper pores all over the place. Love to see this stuff. Right? Connected to the cap with these narrow spokes, and that is just to make reflow that much easier. Otherwise, when you heat up the solder that's on these pads, you've got to heat up all this copper too, so those pads can perhaps not reach temp if you're not careful. And then everything is copper pore, copper pore, copper pore. Now the only other thing that you like to see when you do see all these big copper pores is that they're tied through vias to adjacent layers. And that is to keep these things from becoming big radiating elements. Now, when I say you like to see that, what I mean is it should always be done. We just don't see it here because the designer used micro vias that you can only catch out if the light catches them just right. So these big hunks of copper are tied to adjacent layers all over the place. We just can't see it because they're micro vias, so they're filled in. But they are certainly there. So this designer felt like he had no choice but to use blind and buried vias, which is probably, I'm certain, true with this particular design. It's clean. Wind bond. I don't know that I've seen splatters of paint on any other wind bond thing before. Perhaps those were used in the factory to, as you go through the different stages, you know, did we QC this? Did we program it? Did we check it? I don't know. That's the first time I recall seeing colored paint splots on a wind bond item. Looks like the designers here also kept the copper pulled back from the edges as much as possible. That's always a good thing. You'll get a stronger board since the fiberglass can attach to the fiberglass. I mean, this is definitely a high-speed board. They've done a lot of things. So, okay, let's keep looking. Here's our messy, I couldn't get all of the adhesive stuff off. I don't know that there's much to see. We've got a crystal there. Through-hole vias. Through-hole vias are always cheaper. Even if you have to through-hole and back drill. Is that epoxy for some reason? Okay, and then what else do we have? This is the input-output interface. Again, nice copper edge to board edge clearance. You want a minimum of 12 to 15 mils. It looks like we have well in excess of that. And you can actually see a sublayer of copper there, it looks like. So we've got an immediately adjacent layer of just looking around. Obviously, the designer felt they needed copper pores here too. It can really help with stuff. And you can see some microvias along with some through holes. It's an interesting wander. We've got schmutz, so somebody didn't clean their board. Right, that's flux. Even if you have no clean flux, that doesn't mean you have a no clean board. Crap always gets on stuff during the manufacturing process and acts as a contaminant that can lead to latent failures. So whenever you can, wash that board. Unless you've got a compelling reason not to, like a part that says, "Don't wash me." Well, Keyence, I mean, it's clean looking. I gotta tell you that. You guys are routing a lot of high-speed signals in very little space. I guess my first comment would be this one. You could have put in more copper there just in case that drill wandered north a little, but it's a pretty big drill. I doubt it would wander much. I mean, if these aren't impedance-controlled traces, I'd like to see them a tiny bit wider here on the right, but that's a minor complaint. And you can see the difference in via size between, I wonder if I can get a micro and a regular on screen at the same time here. Probably not. Maybe I get lucky and show you one. Yeah, there we go. All right, so look at the difference in physical size between a regular via, mechanically drilled via, and a laser drilled micro via. The mechanical vias have a minimum drill diameter of 5.9 mils. And that is the smallest drill that we can hole that we can make. After you plate it, it becomes even smaller. We don't go smaller than that because the drills will wander and break. You have to spin them way faster. You know, even as it stands, we're in the 150,000 revolutions per minute. And there's another way to make them. After you do this size, you can do the laser drilled vias, which we can get down to 1 mil. The only difference then concern at that point you have to worry about is aspect ratio. Well, mechanical, it's 10 to 1. So if you're dealing with a, call it a 64 mil thick board, your smallest drill would be 6.4 mils that you would want to use. Now, we would use a 6.5. We would round up or whatever to what we have on hand. But these things can really be just about any size, but they can only go down to the next layer. They've got a 1-to-1 aspect ratio. So if I've got a 1 mil hole, I can only go down 1 mil. If I've got a 3 mil hole, I can go down 3 mils. And that just gets me to my next layer. That's why we don't use these micro vias in everything. You would then have to sequentially stack layer on layer on layer on layer on layer. So, but man, good, clean looking board, Keyence. I've got to give it to you. I like it. Very easy to assemble and disassemble your board for processing. I've got nothing but good things to say. So, good job. And notice too, if we come back out, Keyence went ahead and invested in connectors to make it easy to put this thing together, right? You could make each board, test each board, and then assemble the whole darn thing. Now, that has benefits. Connectors cost a little more? Sure they do. Hand assembly? Yeah, a little bit more. But this is the Teardown DualSys board. Now, if anything goes wrong on this board, you've got to potentially scrap a lot more parts. It'd be much more difficult to rework and fix this than to maybe scrap one of the 3 boards in the Keyence thing. Yeah, you could still have parts that go wrong, things that happen, but it's much easier to replace one of these or rework one of these boards, right? This can be tooled. Put in something, and you could, if you had to. I couldn't do it, but I have colleagues that can. Replace that board or rework it, reheat it, whatever. Much easier to work on the Keyence design than it is the Teardown DualSys design. So there's still quite a bit more to learn about these, but we've been here for about an hour, and that is probably long enough to bore everybody with. So with that, I hope everybody has a wonderful day. Please remember to check out our flexible footprint design. If you want to try to work around the part shortages, you'll find, where is my picture there? There we go. You'll find that in our blog at aapcb.com/blog. And if you have any design questions or you have suggestions for future teardowns, please do let me know. Leave comments in the chat or comments below. Other than that,